So before we move on, any other logistical questions or anything about the stuff we've talked about so far? Okay. We're going to jump right back in. I think that yesterday, if I'm remembering correctly, we were working on a ranking task, and then the bell so rudely interrupted us. Am I remembering that right? Yeah. I feel like that was the case. Yeah. Before we actually do that, I just want to remind us, so that we're all on the same page, because it's been 24 hours, what the impulse momentum theorem is. So the nice thing about the impulse momentum theorem is that the name tells you what it is, right? So we have to remember, though, what these funny words are. So impulse is equal to the change in momentum that is the impulse momentum theorem. But what is impulse? Do you remember? / can you look at your notes from yesterday and find out what it is? Because you maybe don't have it memorized yet, and that's okay. What is impulse? A force acting over a time. So we have a force acting times the time that it acts. The bigger the force, the bigger the impulse. The bigger the time, the bigger the impulse, right? Okay. Either of those gets really big and you got a big impulse. And then we've got change in momentum. So change in momentum, we're just literally going to write delta for change in and P for momentum. We can remind ourselves that this is really like mass times the change in velocity. Okay. The only time this wouldn't be the case is if you actually had a changing mass, okay, which doesn't happen very often. I can't think of any problems in this class that I would give you where the mass was changing. I feel like we maybe talked about this before, but I can't remember. The biggest one that I think of when I think about mass changing is when a rocket is being launched, right? So if you think about a rocket being launched, like a NASA space shuttle kind of thing, it has those big orange tanks on the back, right, which are fuel tanks. And as that fuel gets burned, the mass of the object goes down. Does that make sense? And so it's easier and easier for us to accelerate the rocket as the mass goes down, okay? But we're not going to do problems like that in here. So I don't want you to worry about that. We're going to keep a constant mass and just change velocity. That's the impulse momentum theorem. So if you don't have that written down, write it down now so you've got it, because we're going to refer to that a whole darn bunch today. And then I'm going to bounce back here to the ranking task that y'all started with yesterday, or ended with yesterday. I'm sorry. Oops, this is not the copy that I had for you guys. There it is. So it's been a little while. I don't know if you've had a change of heart. Maybe some of you have. So I'm going to give you just a minute. I'm going to go get you some whiteboards. I want you to take a look at the problem again. I want you to take a look at the answer that you may or may not have stated. You can change it. I'm not holding you to the answer you said before. Okay. Take a minute, have a conversation. If you're at a table by yourself, move somewhere so you can have a conversation with at least one other person. Okay? Take a look there.
Yes, I agree. That's like literally the only problem I've had right now.
So you have 3 or 4 boxes that are filled with different amounts of sand. They're initially at rest. A force is applied to move a box across the floor. The mass of the box with its contents and the net force on the box are given in the figure. Rank the magnitude of the impulse. Again, you just wrote it down on your notes so you can look and see what that means. The magnitude of the impulse on each box for a 2-second interval. Once you've got an answer and once your table agrees, go ahead and write it down on your board. If you need to regroup or rediscuss, please do that. I'll give you just a minute. Go ahead and put your boards up so I can see what your answers are. Should I erase what you had before? Would that be helpful? Okay, we'll just start with a clean one. Here we go. Okay, so we got some answers. We've got A greater than C equals D greater than B. We've got B greater than C equals D greater than A. B, C, D, A, D greater than A equals B greater than C. And we've got D greater than A greater than B greater than C. All right, so we've got 5 boards and 4 answers. Oh, it's on freeze, so you can't see all of the brilliance that's happening. There you go. Sorry about that. Okay. Somebody needs to defend their answer because that's a lot of answers. You felt strongly enough to write it down. Leanne's got her hand up. Go, ma'am.
Because the impulse equals force times time. And it's 2 seconds.
So impulse is force times time, and the time is 2 seconds. Okay? Yeah, and you don't even have to really multiply, do you? Yeah, since the time is the same for all of them. The bigger the force, the bigger the impulse? Sure. Yeah. So the biggest force is D. The next biggest force is A and B are the same. The next is C. Is that this one here? Yeah. What do you guys think? Do you agree with her?
Yeah.
Yeah? Can you talk to me about what your approaches were for those of you that did not say that?
What about mass? Mass have, like,
Does mass have anything to do with it?
yeah.
So that, no, is the short answer. But let's talk. So tell me about what you were talking about with mass. What did you want to do with mass? Go away, thing. What did you want to do with the mass?
Well, like A and B, so they both have 75 newtons of force, and then multiply that by 2 seconds, you get 150. And then you decide one is 2m and then one's m. Are they both gonna have the same impulse though?
Oh, so you know what you were solving for? You were not solving for the impulse. What was he solving for? You were solving for the acceleration. If the question was which rank the accelerations, then absolutely you would need to take the mass, the force divided by the mass, right? Which is essentially what you were doing there. Right?
No, I was doing.
You did force times time, didn't you?
Yeah, but then
and then divided by mass?
I didn't divide by mass. I just I don't know. Would the bigger mass have a bigger impulse or no? Or the bigger acceleration?
Well, let's look at it. So if you've got a force times the time, and then you have so if you have 2 impulses that are in the same, the smaller mass will have the bigger acceleration, right? Yeah. Is that okay?
Mm.
Yeah. So I think what you were doing was not bad physics. It just wasn't answering the question that I was asking.
So forget about mass completely in this question.
In this question, because all you need to know is that impulse is force times time. Now, there are going to be more of them in just a second, right? And so not all of them will be that way, right? That's just in this case, because it says that all the times are the same, and we know that force times time is impulse, then that's just done. Okay. Should we try another one? Yay! Let's do this one.
Yeah.
Okay. So this is another look. It's a different way to look at it. Cars moving along a horizontal road are about to be stopped when they hit a protective barrier. So think crash test for cars. That's kind of what we're talking about here. All of the cars are the same size, the same shape, but they're moving at different speeds and they have different masses. The barriers are all identical and they exert the same constant force. Okay? So once that car hits, they're all going to experience the same force. The question asks you to rank the time that it takes to stop the cars as the barriers apply the same constant force. I'll give you a little while to think. But if I were you, I'd write down the impulse momentum theorem to start. Hooray for the impulse momentum theorem, friends. All right, let me see some boards. Like just waving it up there. D. Jordan, stop moving your board, man. Thank you.
Times 3.
You guys, is that what you had too? Or do you have something different?
No, ours is the same.
Is that one? Okay. You guys had A, D, B, C. All right. Somebody want to defend an answer? Go, friend.
So, what I did, I'll just give an example of what I did for A.
Uh-huh.
The mass times change velocity would be 3,000 times -10.
Okay.
7. And since it's constant force and we don't know the time, I just put the force as 1.
Okay.
And that would mean that it would go to -30,000. And then that would be -30,000 divided by 1. And like basically, when you get that, you're basically done.
Okay. Because what do you know about the force?
It's constant with everything. So it's the same for everything.
Does that make sense? Hold on just a second. I just want to make sure we're okay here. So mass times, so the final velocity in each of the cases is what? What's the final velocity?
0.
It's 0, right? So you got 0 minus 10, which is where you get your -10. Is that correct? So 0 minus 10 gives me my change in velocity. Mass times velocity, that gives me the right-hand side of this equation, right? What does it say about the force for each of the cases? Constant, and it's the same, right? The berries have exert the same force. So that means that the force does not matter. Kind of like in the last one, the time did not matter. Are you with me there? Yeah? So a lot of times it won't say, what is the impulse? But it will say, you need to know that force times time is the impulse so that you can easily figure out what's going on. So, Ben, if I'm understanding what you said correctly, all you did, not all, you did a lot, but the process that you used was the mass times the change in velocity?
Mm-hmm.
Okay. Does that seem okay? So you said A and C are the same. They do not have the same masses. You have 3,000 times 10 and 1,000 times 30. I see. Okay, yeah. Does that seem okay? Okay, got one more for you. With the top one or the bottom one. They're very similar. Who wants it? Who's going to pick? Top or bottom?
We're on top, yeah, we're on top.
All right. Fantastic. Here you go. So this is kind of like the little carts that we had when we were doing our tracks. Do you remember if you accidentally hit the button and the plunger came out? So it's kind of like if you have the plunger out. So you've got carts with a spring plunger run into a fixed barrier. The carts are identical but are carrying different loads, so have different masses. The velocity of the cart before and after the impact are given. So just to make sure this makes sense, this is the 10 kilogram cart before, it's moving at 4 meters per second, and after it's stopped. Here you've got the same cart again, etc. Rank the change in momentum. Go. Do it. You got this.
A lot of numbers.
You can handle it. You can probably do them all in your head, too, if you try. I mean, I'm not saying you have to. I'm just saying it is likely true. All right. Boards up. Show them what you got. Oh, nope. Yep. Pull. Okay, let me write these down. So I see answers like that. I see answers like A, B, D, C. Ben, are you going to commit to something? Okay. Let's find out what's going on. Talk to me. So I see both all the same and a ranked A, B, D, C. Defend your answer, please. Go.
Okay, so in the equation for the conservation of momentum,
Yeah.
You do the mass times the initial velocity, and that should equal the mass times the final velocity. So if you do in A, the mass is 10 kilograms times the initial velocity is 4. That's
Okay.
40 kilograms meters per second. And then after is 10 times 0, which is 0.
Okay.
So you get a change of, or the magnitude is 40 kilograms meters per second.
So the change in momentum is negative 40 in this case, or no, positive 40.
Yeah. That's,
No, negative 40. Whatever, it doesn't matter. Yeah, because all we care about is magnitude. You're right.
and then B, 10 times 3 is
Yep.
going to be 30 kilograms
Yep.
per second. And then 10 times negative 1 is negative 10. 30 to negative 10 on the number line is negative 40.
It's negative 40.
And then the same thing for C, 20, negative 20. And then D is 25, negative 15.
How are we doing? Is that making sense? Ryan, you look
No, I was just looking at the.
like you don't. Okay. Oh, gotcha. Okay, cool. All right. Is this kind of okay? Okay. The reason that I like these kind of problems, you guys, is because I don't want you to always get bogged down in all of the numbers without being able to just kind of like think big picture about how you would solve this kind of problem. Okay. We have just a little bit of time left because time just, keeps on ticking away. I had in my list of things to do to go over some homework. Did you guys did you all, have any questions about 218 number 4 or 195 number 2? Were there issues or did they go okay? Number 2, 195 number 2?
Yeah.
Sure, we can do it. Page 195 number 2. Let me open up my book. So problem number 2. Oh, it's funny that I gave you this one. Because I read it again today and I was like, oh, I don't really like that question. Let me think about it for just a second. Can I do this one, Leanne? Can I do this one after we do one more?
Yeah.
Is that okay?
Yeah.
This one is actually more complicated than I realized it was because I was reading it again this morning. I'm like, oh, this is a little harder. So let's go through one other one first. If that one doesn't end up making a whole lot of sense, I don't want you to get bent out of shape about it. Is that fair? I want to look at 195 question number 1. Let's do that first. So 195 question number 1, if you don't have a textbook in front of you, I'm just going to read it to you just to save time. It says, so make sure you're writing down your givens as we go so that you've got it. So it says a 0.5 kilogram football is thrown with a velocity of 15 meters per second to the right. The stationary receiver catches the ball and brings it to rest in 0.02 seconds. What is the force exerted on the ball by the receiver? So the givens, because we always start with our givens, right? We always do that guess method, always start with our givens. The mass of the ball was 0.5 kilogram. What was the initial velocity of the ball? Did you guys catch that? 15 meters per second to the right. So we'll just call the right positive. I think that's okay. The final velocity for our football is going to be, what did it say? It says a stationary receiver catches the ball and brings it to rest. Yep, so it's going to be 0 meters per second. But he does that in a time of 0.02 seconds. And they want to know the force. Now, looking at that list, you might be like, oh my gosh, that looks like a lot of scariness to do. But let's just think about this and not get too angry or upset about it. The impulse momentum theorem says F times T is equal to M times change in velocity, right? Is that okay that I wrote it out like that? Change in just means final minus initial, just like you all just told me on that last problem. Mass, initial velocity, final velocity, time. Do you see that we have everything here except the thing we're looking for?
Mm-hmm.
Everything in this equation is right there. Poof. So life is good. So we should be able to solve this pretty darn easily. If we want to plug numbers in, because I feel like that's often what y'all want to do. I will humor you this time. 0.50 kilograms, a change in velocity. So the final is 0. The initial was 15. We're going to use our fabulous problem-solving skills. 0 minus 15 is?
Negative 15.
Negative 15. Negative 15 times a half.
7.5.
Yep. Negative 7.5. So this is equal to negative 7.5 kilogram meters per second. So that's the change in momentum. That's the final momentum minus the initial momentum is negative 7.5 kilogram meters per second. And that was a force that was applied over 0.2 seconds. We doing okay with this? I'm going fast because I just want to make sure we get to the one that Leanne wanted to talk about too. Our times are going to cancel. We can solve for force. Okay. The reason I wanted to focus on this today is because your homework for tonight is going to look a lot like this kind of stuff. Okay. So force is going to be equal to, I don't know, somebody get an answer for that?
375.
375?
What are our labels on that?
Well, I don't know. It's a force.
Can we go through like the kg?
Oh, for sure, for sure.
Yeah.
Yeah. So it's kilogram meter per second divided by second, right? So if we think back to our love of fractions and dividing and multiplying fractions, right? We love it. The denominator and the numerator could just go to the denominator, right? So that means that you've got kilogram meter per second squared, and a kilogram meter per second squared is a Newton. Yep. Yep. It's the unit of force. Yep. So you can write it as kilogram meter per second squared or kilogram meter per second per second. It's a lot to write instead of just an uppercase N, but whatever makes you happy.
Put kilogram per Newton, or do you put just the Newton?
It's just a force.
Okay.
So it's just a Newton. Yeah, it's just straight up old Newton. We okay so far? Okay, so now I do want to look at the one that Leanne had. The reason that I was a little hesitant is because it requires a little bit of physics. Now, it's physics that we've done and we know, but it's been a few days since we've done it. So this is page 195, question number 2. It says an 82 kilogram man drops from rest on a diving board 3 meters above the surface of water and then comes to rest 55 seconds after reaching the water. What is the net force as he is brought to rest? That is weird. So sometimes when I'm trying to do these, right, and the question doesn't make sense, like with the football question, it just kind of laid out all your givens. So you're just like, boom, 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 you're done. With a question like this, it's a little more overwhelming to me, so I'm going to draw a picture first. When in doubt, I'm going to draw a picture. So I'm going to grab my little diving board, and then I've got the water below. And so I've got my person. There's the person, and he's going to jump down, right? And he's going to fall, free fall from rest. What was it, 3 meters or something like that?
Yeah.
3 meters. So his initial velocity here is what?
0 meters per second.
0 meters per second. But by the time he gets to the water, he's got some other velocity, doesn't he?
Mm-hmm.
Yeah. Now we can figure out what that velocity is using our kinematics stuff, okay? But we have to think about that, because when is he feeling the force that's going to stop him? Or is it a him or a her? Do we know? Unless I'm making assumptions here. The diver.
Yeah.
What force is acting on the diver to slow them down?
At impact or in
Well,
the motion of falling down.
So the diver is going to stop down here, right? As the diver falls from here to here, what happens to his speed? Its speed. Their speed. Excuse me.
Reduces.
From here to here?
Oh no! He gains.
The diver's going to increase in speed, aren't they? Excuse me. I'm trying to use nice gender neutral language. So as the diver falls from here to here, their speed increases. From here to here, what happens? Stop, so it slows down, right? I don't know. Have you ever watched anybody dive into a pool? Like, I think they're okay, right? Like, assuming the diver can swim.
You have to do a swimming test before you go on
Right, that's true. Absolutely. So we will assume that this diver has passed this. I mean, like, call it a diver. So, like, probably okay. Does it make sense that the water's pushing up on the diver? Yeah. That's the force that we're talking about. So we really want to know the force that's pushing up. I want this color. The force of the water. Okay. That's the question. What is the force of the water if it takes a time of 0.55 seconds to stop? The force of the water is our question. So in order to figure that out, we need F times T is equal to M times velocity final minus velocity initial, right? Yeah. The force of the water times 0.55 seconds. We know the mass of the diver, I think, right? It says 82 kilograms. What's the diver's final velocity in the water? 0, right? What's the diver's initial velocity? What's the diver's initial velocity when this force starts to act on them? What's the diver's velocity when they get right here? It's something.
Yeah, it's something.
We don't know what it is, though, do we?
Yeah.
This is why the problem is harder. Because we have to find the velocity of the diver, which we can totally do, and we're going to get done because we've got a couple minutes still. We want to find the velocity of the diver right here. This is our VI. So we've got an initial velocity at the top of 0. A velocity at the water is our question mark. We know that they've fallen a distance of how much?
3 meters.
Mm-hmm. And they've done so because of some acceleration, right? Negative 9.8. So you pull out those fancy orange sheets. Oh, yeah. It's good noise, right? It woke you up a little bit if you weren't there yet. Initial velocity, final velocity, displacement, and acceleration. Do you have that relationship somewhere on that orange sheet?
Yes.
Yes. What is it, Leanne?
The distance equals half of plus VI times T. Is that right?
That one has T in it.
Don't have T?
We have this T down here. This is why it's a complicated question. I don't know how long it's going to take. We could calculate it.
Oh, wait.
Is there one that has squareds in it?
Yeah.
Yeah, let's do that one.
VF squared
There you go.
equals VI squared plus 2A.
Yeah. Yeah. So you can find the final velocity, initial velocity. So you're going to take 2 times negative 3 times negative 9.8. Can you do that real quick? You got a calculator in front of you? Go, go, go. You will not have a question this complicated on a test. Just making that clear. Unless you really like one, I could definitely put one on there. I just don't think that would be a fair assessment. This would be a good, big picture assessment. How much do you know, really? But I'm not going to put it on a test for you. Did you square root it? Square root it. And there shouldn't be negative because you have 2 negatives in there.
3,407. Oh, sure.
That's too fast. I would never jump off a diving board if I had to go that fast by the time I hit the water. Holy cow. So it's going to be something on the order of this is going to be 50. So I don't know. Something about 7-ish.
Yeah, 7.67.
7.67. Okay. This number here goes right there. We're not done.
Oh, God.
This is why I shouldn't have assigned this problem.
I thought we were done.
No! We're only halfway there. But we're almost there, really. because you're looking for the force. You know the time, you know the mass, you know that velocity now. So now you just plug it in. Josie, are you doing okay? Yeah. Okay. I just want to make sure that it wasn't me that was causing your reaction there. Okay.
Not very good.
Are we doing all right? So F is going to be equal to the mass of the person was 82 kilograms. I did not do a good job of writing my givens down in this one. I'm sorry about that. Times the velocity of 7.67 meters per second divided by the time of 0.55 seconds. And from that, you can find a force. It's a pretty big force, friends.
Can you forget about the negative in the velocity?
Oh, good call. So this should actually be a negative, right? Because he's going downward at negative 7.67. Yeah. So then minus a negative is going to give you a positive.
Oh.
Does that make sense?
Wait.
Did I mess your brain up, or are you okay?
No. He's going down. So
He's going down.
That velocity is negative.
It is negative. That's this velocity here.
Leave it as negative.
Leave that so it's going to be negative 7.67, but it's 0 minus negative 7.67. That gives you positive 7.67, which is good because if he's falling this way, the water is pushing up. Is that okay? Water pushes up, so that means he slows down. We've done this before. 1,100 something?
It makes sense because water is.
Yeah. So just really quickly on the homework for tomorrow, 194, questions 3 and 4 should be doable. These ones are kind of like the question 1 that we just did. They're from the same page. 195, questions 3 and 4 are just like the one that we did before. And then 197, number 2, that one you will have to use a little bit of kinematics. So for this one here, get out that equation sheet. Again, on a test, I'm not going to ask you to do the kinematic stuff because I want to just assess how you are doing with the impulse momentum theorem. But for now, okay?
Would you do that for your AP class?
Oh, yeah.
You put stuff in.
Oh, for sure. Oh, yeah, because they're going to take an AP test at the end of the year.
That's like.
And it's all put together. So it's kinematics. Like you have a projectile motion problem where then you have to figure out the impulse acting on it when it hits the ground. And yeah, it's all integrated.
Adding up on it.
Yeah.
But we're just kind of like.
You can leave them out. That's fine. Thank you for asking.